You know, one of the most important special cases of an accelerated frame is a frame that rotates. Okay, in other words, you're doing a circular motion. This is very important because of the Earth itself is doing circular motion about the sun, and as you know, any person standing on the surface of the Earth is actually doing circular motion due to the spin of the Earth as well. So let's look at an object doing circular motion. Okay, an object doing a circular motion. Let's say a car doing a circular motion. Let's look at the motion of this car. If I use the car as a reference frame, this car going forward, okay? If I use the car as a reference frame, obviously that is a non-inertial frame because the car is accelerating. Okay, the car is accelerating. Let's say the car goes forward at a constant speed. Then of course it is only subject to a net force which points toward the center of that circle. That is called centripetal force. That is a real physical force. It can be provided, for example, by friction, by part of the gravity, or whatever. It's a real physical force. Okay, F, centripetal. Centripetal. That is one force. And if you stand by the side of the track watching this car, if you manage somehow to measure using remote sensors, you measure the net force on the car, you'll find this much value. How much is it equal to? It equals to V squared M V squared over R. The direction is into the center of the circle. Usually what I do is I use a unit vector pointing from the center of the circle outwards. We call it unit vector along R, so here is negative because it goes backwards. That is the real force, right? Now, if you were the driver of that car, however, you will be living in a non-inertial frame of reference because the car itself is accelerating. Okay? So from your point of view, how do you understand what's happening? Well, you find yourself not moving at all, right? Because relative to yourself, you're not moving. So what is your acceleration? Zero, because you're not even moving. Of course, you don't have any acceleration. And yet, somehow, you'll find that you are subject to a force from the seat belt, you know. And anyhow you add it, you'll find there is actually a measurable, real physical force pushing you to the center of the circle. And then, of course, we know that force is required because you are actually moving in a circle with a speed v. But the thing is, you don't agree with that, do you? You don't believe that you're moving, right? From your own point of view, you're at rest. And yet, you still detect this force. So, you say, gee, something's wrong here. I have no acceleration, and yet I'm experiencing a force. How do you explain this? Right? That's the question. How do you explain this? Well, the way you explain this is to say, all right, I must balance this force with another force. These two forces cancel out. That's why I am not moving. I have no acceleration. And that force obviously has to point outward. Okay? What is the magnitude of that force? Well, it has to cancel with the real physical force. What's the direction? It has to be radially outward. It has to point away from the center of the circle. Instead of center seeking, you're trying to avoid the center. You're trying to go away. And that force has a name. It's called centrifugal force or centrifugal force. Okay, so I'm going to add that. How much is that equal to? That equals to mv squared over r, same magnitude, but along the radial direction. Centrifugal means going away from the center. Instead of centripetal means seeking the center. Okay, so these two forces have the same magnitude, opposite direction. They act upon you simultaneously, and therefore you say the net force is zero, therefore I'm not accelerating. Perfect, Newton's second law is valid. Zero force gives you zero acceleration. Okay, that of course is not a real force, right? It's a fictitious force. Does this force really exist? No. How come I still use it? Because remember, that's the price I pay so that I can still manage to use Newton's second law to explain what's going on, even though I'm in an accelerated frame of reference. Okay, that is centrifugal force. So suppose you are observing what's going on from the perspective of a rotational frame that itself is doing circular motion. Okay, like a carousel that's rotating. In order to understand the motion of an object from your perspective, you must introduce a centrifugal force along with the real physical forces. That's how you interpret the motion of an object. So therefore, it is a very common force. Now, let me ask you this. You have centripetal force and you have centrifugal force. They obviously point in opposite direction, they appear and disappear simultaneously, and they have the same magnitude. That seems to remind us of the concept of action and reaction, right? Newton's third law says any force is always accompanied by its reaction. They have equal magnitude, opposite direction, and then appear and disappear simultaneously. That seems to be, what centripetal and centrifugal force satisfy, right? They have the same magnitude and opposite direction and so forth. So, is it true then that centrifugal force and centripetal force form a pair of action and reaction? What do you think? Well, first of all, let me ask you, action and reaction, do these two forces act on the same object, or do they act on different objects? Well, we learned Newton's third law, right? You have object A and object B. A gives a force to B, B gives a force to A. Here's F, here's negative F. Action and reaction. You see, they are exerted upon different objects. Is that the case here? No. These two forces are exerted on the same exact object, the driver or the car, whatever, right? So that's not the case. And secondly, these two forces, unlike action and reaction must come from the exact same physical origin. Okay, so for example, if this is a book and this is the table, a book sits on the table, the book presses the table down with a normal force. The table pushes the book up with a normal force. Both action and reaction are exactly the same physical origin. They're both normal forces. Here, the centripetal force is a real physical force. It can be provided by tension, by gravity, by friction, whatever. The centrifugal force is totally different. It is not even real. It is pseudo, okay? It does not even exist. It has totally different physical nature. It is introduced out of convenience so that we can use Newton's second law, even if we're not supposed to use it. So this is not a pair of action and reaction, okay? Please be careful about that. Another very important example of fictitious or inertial force is the so-called Coriolis force. Coriolis force also refers to the situation where the reference frame itself is rotating, like the Earth, for example. If you stand on the surface of the Earth, you're rotating. If you're using your own perspective, that's a rotational frame of reference. But unlike centrifugal force, which always exists, the Coriolis force existed only if an object in question, being observed, is actually moving relative to that rotational frame of reference. Okay? So let's consider the Earth, for example. Here's the equator, North Pole, South Pole. The Earth spins from west to east. And here's a meridian, here's another one. Now, if the Earth did not spin at all, there's a baseball here. Okay, there's a baseball here. So if I throw the baseball aimed at North Pole, if the Earth did not spin at all, it's going to end up somewhere there, right? Somewhere there, on the exact same meridian, from here to there. But that is not the case. The Earth is actually spinning. Okay, the Earth is actually spinning. So what happens when the ball is airborne? Suppose you still aim at the North Pole, but you launch the ball. When it's airborne, what's happening to the Earth? The Earth is actually spinning, right? It moved forward to the east. So now the question is, where is the ball actually going to land? So what do you think? Well, you might think the ball is going to land somewhere on the west, because after all, the ball tries to go this way, and yet the Earth has moved eastward, right? So shouldn't you end up somewhere to the west of your intended landing spot, which is here? Well, think a little harder. Okay, here's the thing. Before you throw the ball, you're standing still in a ballpark somewhere here. Okay, this is a lower latitude. You're throwing something towards a higher latitude, right? Now, in the lower latitude, you're closer to the equator, assuming this is the northern hemisphere. Okay, the northern hemisphere. So you are actually initially moving in a circle like this. In a circle like this. How long does it take to finish that circle? 24 hours. Okay, since you're not moving relative to Earth, you're standing still. That means you're actually having a velocity this way, right? Otherwise, you'll be left behind as the Earth spins. And this is the velocity of anything that is stationary at this latitude, including the baseball before it was launched. That is, of course, measured relative to the center of the Earth, the center of the Earth. Now, the intended landing spot is at a higher latitude. In a higher latitude, an object would be moving in a smaller circle, right? Smaller circle like this. And it still takes 24 hours to complete that circle, which means any object standing still there would be moving with a smaller eastward velocity because it finishes one side, a smaller circle in the same 24-hour period. Okay? Let's say, for example, from here to there, at this point, there is a certain eastward velocity. The baseball would have that eastward velocity to begin with, but the landing spot is moving forward, moving eastward at a lower velocity eastward, right? So as the ball is airborne, both of these points are moving. The baseball moves with a greater eastward velocity because the same eastward velocity at the launch point. The landing spot moves slower towards east. So what happens as a result is that the baseball is going to move somewhere ahead. It's going to land somewhere there, okay? Maybe not far, maybe not that far, but the idea, you get the idea. So the baseball will veer towards east. It's going to veer towards east. That is, of course, you are throwing the baseball in the northern hemisphere, towards north. If you observe that baseball, you see, gee, something's funny. Somebody's pushing it to the east. Is somebody pushing it to the east? Really? Nobody is pushing it to the east, right? This force, if you attribute that to a force, that is a pseudo force. It does not really exist. But it looks very real to you because you're in a rotational frame. So you attribute it to a pseudo force. That's how you explain the eastward movement of the baseball, and that is called the Coriolis force. The Coriolis force. As a matter of fact, if you're in the southern hemisphere, the effect is just the opposite. Because you try to throw a ball in the southern hemisphere, still going north. Okay? Again, your intended path is like this, from here to there. But this time, you start from a smaller velocity eastward to a larger velocity eastward because the landing spot is closer to the equator, right? So the baseball where airborne does not have enough eastward velocity to keep up with the velocity of the landing spot. It's going to lag behind, therefore it's going to land somewhere to the west of the intended spot. So you see, the effect in the northern and southern hemisphere are just the opposite. Okay? You launch this thing, or airborne, it's been pushed to the east, but of course if you launch it backwards, it's been pushed to the west. So the idea is if you take a bird's eye view of the path, you'll find the path, if it's launched in the northern hemisphere, the path always is going to veer towards right. Okay, veer towards right. Suppose, you want to go this way. Okay, you want to go this way. Somebody's always pushing you to the right so that you end up going like this. In the southern hemisphere, you always veer towards the left. So suppose you intend to go this way. It's as if somebody always try to push you to the left. You can attribute that to a fictitious force called Coriolis force. Okay, this is, generally speaking, this is a fairly small effect because it has to do with the acceleration due to the circular motion of the Earth, and that is a small acceleration compared with the acceleration of gravity, because after all, the Earth takes 24 hours to turn around, right? That takes a lot of time. So therefore, it's usually a small effect, which is why as you walk, see, we live in the northern hemisphere, right? As we walk, do we feel somebody's pushing us to the right? No, we don't, because the force is extremely small. We don't notice it at all. However, Coriolis force does play an important role in weather phenomena. Hurricanes and typhoons, for example. We're talking about a piece of cloud, okay, suspended in air for a long time. It can be weeks or even months. As the cloud moves, it's subject to the Coriolis force if we want to observe the movement of the cloud from the Earth's point of view. It is going to veer towards right if it's in the northern hemisphere, and veer towards left if it's in the southern hemisphere. This can have very important consequences for the formation of hurricane and typhoon. For example, in the northern hemisphere, how does a hurricane start? Well, you start with a local region of low pressure. Okay, so this region, somehow the air pressure loss balance is lower than the surrounding air pressure. So what happens? The surrounding air is then going to come in, right? They're going to come in to fill the void because the surrounding air has higher pressure. Now, without the Coriolis force, the movement is more or less radially inward. So before you know it, the air will rush in to fill the void and you have balanced pressure. This radial movement is not going to cause any devastating hurricane or typhoon like the Katrina. But what really happens, if I'm talking a bird's eye view, okay, so I'm looking at this weather phenomenon from the sky, from the space, and then what I found is that due to the Coriolis force, Coriolis effect, the actual movement is not just radial, rather it is being pushed somewhere to the right, so it starts to do this, do this. Even though that force is small, you accumulate it over a course of a few weeks or even a few months, it can be actually significant. So it's going to start a rotation. See that? It's going to start a rotation faster and faster and faster. There is a counterclockwise rotation of airstream taking a bird's eye view. And when rotational speed is very high, you have what's called a hurricane. If it's in the Atlantic, if it's in the Pacific, we call it a typhoon. Really, it's the same thing. So all hurricanes and typhoons generated in the northern hemisphere would turn counterclockwise when viewed from the space. That's how these things are formed. Okay, in the southern hemisphere, if hurricane and typhoon were to be formed, it would rotate in the opposite sense because the Coriolis force is just the opposite. All right, that is the reason why we have these hurricanes and typhoons. So what about the equator? The equator is the borderline between southern and northern hemisphere, right? And the Coriolis effect is just the opposite. So what's happening on the equator? If something is formed on the equator, if a low pressure center is formed on the equator, the surrounding air will come in. How is it going to turn? Clockwise or counterclockwise? Well, guess what? It cannot make up its mind, right? Because it's straddling the border between these two hemispheres. So it's not going to spin significantly. That's what happens. So what does that tell us? Hurricanes and typhoons cannot be generated on the equator. The equatorial region is actually relatively calm. Of course, once a hurricane or typhoon is formed, it can actually be blown across the equator, at which point it's going to slow down because the effect has been reversed. But it can actually sweep across the equator. But you do not expect a large-scale hurricane or typhoon to be generated right on the equator because it doesn't have the Coriolis effect to help it.